I'll have 15 minutes left, and I hope my voice will survive that part. But maybe just as kind of a teaser, if you want to kind of talk about the second part, or maybe let's step back a second to think, okay, what just happened? Because Aaron's break helped, but maybe now you need a moment to get into what we just did. And I just showed you this kind of very small toy model of the first layer of attention, where there were these two kind of mechanisms based on which part of the input was used. And then we looked at like how do they change, or which one is the better one depending on the sample complexity in terms of training loss, and then how they change. And as I was mentioning, there's kind of some follow-up work by some colleagues that looks at the setting with multiple layers and actually looks at the dynamical part and not just the statics. But kind of the motivating question that I'm interested in are these phenomena. So I'm kind of interested in where do similar solutions occur in realistic settings. And that is what the second part would have been about. So there you actually look at a specific task where you take an input sequence and you want to solve an algorithmic task, in this case counting, so how many tokens are in the sequence. And you will find that kind of for this task, which is kind of a canonical way about thinking of if you want to kind of extract and select similar information from your input and then kind of aggregate and measure it to give a count, how this is implemented. And I think the answer is that you can solve this with a small transformer, but you can actually see that there are different kinds of solutions that are in the loss landscape that have these properties. That what you see here is kind of the attention matrix that you're learning. And in the top line is one implementation, 1 point in weight space, which is kind of independent of the sequence that you're putting in, whereas kind of the second point kind of assigns independent of the semantics, whereas the second point assigns kind of the score depending on whether the two tokens that you are comparing are the same or not. And I'm very happy to talk about this more with a low voice after this talk, if you're interested, because there's kind of a nice picture of how kind of learning the specific task and the different solutions depend on the architecture. So small modifications that you can make to this one layer thing that kind of change what you learned. And in some sense, it's kind of nice to be connected also to what Aaron is looking at, in the sense that you do not only want to understand that the performance is the same, but kind of that the mechanism internally is the same. So this is kind of a nice connection. But I'll skip over this for now, because I already feel that maybe we don't have so much time. So let me just kind of skip over to the third part here, because I think there are some nice questions and connections to kind of work we've seen so far. And the questions I want to look at here is a bit more on actually trying to find a null model, how you would represent data structure when there is no structure in the data. And I'm going to use data set distillation as a framework for this. And as a reminder, there was kind of already this nice talk by Bingbin on Monday about distillation, where she explained the idea that you, instead of kind of directly training from scratch with your data, you train a student on a teacher that already learned a given concept with soft labels. So kind of the full vector in this classification task, so that you can achieve compute efficiency, so you're training faster, or you need less data, and you can, or like in the case of knowledge distillation, you kind of want to train a smaller model. And data set distillation in that context is that you want to remove mainly the number of samples to achieve the same accuracy, possibly for kind of the same size of the model, but kind of maintain your performance. And you can also do this using the soft labels. Of course, there are like different techniques of kind of achieving this goal of reducing the number of samples. You can delete duplicates. You can kind of do different techniques with pruning. But like even for big models, it was recently shown that if you use those soft labels, you get a good performance that is kind of on par with specialized methods. So in this case, the authors of this work trained kind of a student on teacher data for ImageNet. And there are kind of all of these different methods that are specialized for dataset distillation, but kind of this random baseline, kind of the red curve, where you just kind of select random items from the distribution, kind of weighted by class, but you give the soft labels and nothing more. It's kind of still the best thing you can do. So there's really some sort of power that lies in the soft labels. And as mentioned in the talk on Monday, the data structure is really important there to make it work. So on Monday, we saw that kind of at these different times in training, you kind of use the teacher information in the soft labels to then kind of get to the right solution. But at the same time, models that learn stuff, they don't only learn data that is inherently structured, right? So for example, in a language model, you might want to recall facts that are in some sense not super structured, but like arbitrarily memorized. And then the question becomes, what information do these soft labels actually contain when you trained your network in this regime where it memorized something? And kind of in this work, what we did is we looked at random data that is actually where you can actually only memorize it as kind of the null model to test what happens when you kind of have no structure and your data is a priori independent. And what we do, and I mean, kind of famously, this is kind of a nice model that shows the power of networks, because they're actually really good kind of doing this task. So if you shuffle like data sets around with the labels, you're often still able to memorize them with the capacity that we have. And then the question is, if we train a teacher to actually memorize information, can a student then actually generalize on this? And what I mean by this is that if you consider a task where your input data is kind of IID samples, there's no meaning in it, it's just some vector, and then you sample an input label, also like from a number of classes, IID, and then you kind of compose a data set of n samples, and then you compose like kind of an extra set that you don't show to the teacher, just to check some things later on. Then you train the teacher on this data set, and it memorizes it at 100%. And then kind of, because there are no correlations a priori, the kind of accuracy you get on this held out data would be random guessing. It would be like, yeah, you can't learn it, right? There is no connection. But then when you train a student on the soft labels by matching the logits and kind of need to select your temperature high enough, and then you divide your memorization data set into two parts. So kind of a teacher training, a student training set or test set. And in data set distillation, you would usually call kind of the set that the student actually sees a transfer set or a core set. And then the question is, how good is the student on these different types of data? So if I trained it on kind of this part, will it learn anything more about the test than about that kind of goes beyond this random guessing?
So here the labels are independent of
yes.
X. Okay.
Everything is uncorrelated a priori, and kind of the only correlation comes through the fact that it's learned by the teacher. Any more questions? So you can run this experiment for kind of this random fact setting with a big model. So you kind of take 3 numbers, sample each of them from 1 to 1,000, just kind of put it in as an input, and then you train a classifier on top of like a pre-trained network, but you actually like train the whole thing. And you fix your data set to a given size. And then what happens is that actually the performance on this held out data that the teacher saw but you didn't see is very much non-trivial. So here we have like 1,000 classes. So the trivial accuracy would be like super small on the scale. But what happens is that as we train the teacher, we go to like 100% accuracy on this training set. And then at the same time, we kind of get better on the unseen memorized data that the teacher saw. And of course, on the generalized, like on this set that the teacher also didn't see, we like stay at random accuracy. And to look at this phenomenon maybe a bit more visually, we can also kind of reduce the size of the model extremely down. And we can look at this 2-dimensional data here. So 60 data points, 3 classes. They lie in this 2D grid. And we can kind of do the same exercise of holding out 20 of the data points and training a student on it. And what happens is that a student, kind of if you repeat the experiments, you see that on average you get like a much higher accuracy on the data that the teacher saw versus kind of held out data. So kind of 1/3 is the accuracy you get on stuff that's uncorrelated. And the decision boundaries in this 2D space, they kind of look similar. Yeah?
By the way, so here, you're giving it the logit in this case.
So what I'm doing, yeah, I should have probably written this down, is that I take the logits of the teacher and I apply a softmax with the given temperature. Because if you don't take the temperature high enough, you don't see this behavior. More stuff to be made more precise.
Because then you would be training on. Because if the temperature was too low, you would be essentially training on hard labels, and then,
exactly.
Yeah. Okay.
Yeah. Yeah. So then it becomes uncorrelated again as you send the temperature to 0. Yeah. Yeah. So. Yeah, so there's this phenomenon that you kind of get this. So there must be some information in the soft labels that transfers from kind of the memorized ones to the held out ones. And if you kind of reduce this further and you look at kind of binary logistic regression, it's actually a bit easier to understand what's going on. Because in that case, if you're in the binary case, what you can do is you can train on logistic regression, again, on like your uncorrelated data set. Here you take Gaussian data and like the 2 classes. And then kind of the equivalent is just, so what we did here is we just take the logit and then actually like this becomes linear regression, right? So in the sense that there is this known threshold that a teacher cannot memorize more data than, more 2 times the samples than the dimension, and at the same time, so kind of on the x-axis here is like how much of the data does the student actually see. So as I increase up to here, it sees like almost the full data set. And then there's kind of this transition where you can actually get 100% test accuracy by the student, because as the student has seen enough of this like data points with logits, like your linear regression becomes invertible. And then you're kind of in this regime, this green regime where you can actually say like, okay, there's 100% accuracy simply because the teacher structure is clearly defined. There's like only one solution here. And then kind of what this would suggest maybe is that what we saw before is a similar behavior in the sense that we can actually generalize on the teacher structure because of the soft labels are kind of defining the solution in these models. But what you can see if you kind of scale this experiment up to like a nonlinear model, so like okay, yeah, and with more classes, this is kind of similar. If you take multi-class logistic regression, then kind of the phenomenology for kind of a nonlinear setting looks similar. So here I'm kind of not only scaling up the model, but I'm also scaling up the number of classes. And then kind of see a similar behavior where there's this kind of border where the teacher capacity is not enough to memorize the training data, so we don't care about kind of what happens after here. But before that, there's also this region where you achieve 100% accuracy through your memorized data. And before that, there's kind of something that's better than trivial, so some kind of weak learning going on. But like not to 100%, so a bit in the sense that of what we saw with the other models. But what kind of changes here is that while we still have this phase where you kind of get 100% accuracy on what you memorize, and then there's kind of this, I would say, statistical leakage of information that you didn't see, that you would learn from the teacher. There is this intermediate phase before you get to 100% accuracy, where your student doesn't remember, doesn't memorize, doesn't learn all of the data in its training set, because it's harder to memorize kind of the logits with the inputs than just the one hot encoded vectors. So the capacity of, like the relative capacity of the teacher to the input data and the student to the input data with the soft labels is a bit different. So you kind of arrive here, and then at some point when you kind of have enough, like high enough sample complexity that you can identify the teacher, you kind of first go through this phase where like you statistically learn a bit about your held out data, and then at some point you generalize here on this teacher structure and you arrive at 100% accuracy. And then, okay, afterwards you don't do much. And this kind of this line here, where you start to, or where you stop to memorize your training data as a student, like strongly depends on the temperature, right? Because what Sebastian said before, like you need more capacity to memorize soft labels at a high temperature than at a low temperature. So kind of this curve can move a bit, and yeah. And so what we're hypothesizing is that the behavior that kind of I showed you in the beginning for the larger models is not actually kind of this generalization to the teacher that's going on, but it's rather kind of this statistical leakage that just kind of takes the local similarities of these models here. And since this is kind of purely empirical, so like we only did experiments, we don't have any closed form solutions for these lines, because it's kind of hard to have a teacher-student setup where your teacher comes from something that is learned, right? Yeah, we don't have like a theory for this, but it would be kind of interesting to see, maybe at least for kind of the multi-class case, also in the regression case, how all of these are rescaled. Yeah, and I think this is kind of the small, curious example of this distillation setting where you don't use structure, but yet you can actually have this sort of generalization ability, or like statistical similarity ability that you could take into account when you're interpreting why these bigger models actually succeed at data set distillation. That it's not only about the structure. but also because the teacher correlates the inputs in a very specific way. Yeah, and I think that's kind of all I wanted to say about this. And I'm glad I managed to keep my voice until here. So yeah, I think, again, if you want to kind of talk about how counting is implemented in these networks, I'll be happy to chat as well. Thanks a lot.
Question.